So imagine a chemist gets handed this mysterious white powder. How in the world do they figure out not just what's in it, but the exact percentage of every single element? Well, it's not magic. It's actually a fascinating field of chemical detective work called quantitative analysis. And today we're going to pull back the curtain on the classic techniques they use to crack the case.
Right, so that's the big question, isn't it? How do you measure something you can't even see? We can't just peek into a compound and count the atoms of chlorine or sulfur. The real challenge is to come up with a clever plan that forces these elements to show themselves in a way we can actually weigh and measure. That's our mission today, to figure out a compound's true identity.
And the master plan for this whole mission is a brilliant, elegant three-step process called gravimetric analysis. It all comes down to weight. First up, oxidation. We use some seriously powerful chemicals to completely demolish the organic compound, which sets our target element free. Then, step 2 is precipitation. We cleverly cause that freed element to react and form a brand new solid, pulling it out of the mix and isolating it. And finally, the easy part, calculation. We carefully weigh that solid and use some simple math based on atomic masses to find the exact percentage of our element in the original sample. So it's break down, isolate, calculate. That's the core strategy we're going to see again and again.
Okay, let's put our strategy into action. First case file on the docket, tracking down halogens. We're talking about elements like chlorine, bromine, and iodine. So how do we apply our master plan to these guys? Well, the key piece of gear here is called the Carius tube. Think of it as a heavy-duty, thick glass tube built for some pretty intense chemistry. Inside, we put our organic compound along with two crucial reagents, fuming nitric acid, that's our chemical sledgehammer, and silver nitrate. We seal it up, heat it, and the intense pressure and acid just obliterate the organic material, releasing the halogen. But that halogen has nowhere to run. It immediately reacts with the silver nitrate, which traps it as a solid silver halide. And that solid right there, that's our golden piece of evidence. Now that we've got our solid evidence, how do we connect its weight all the way back to the original compound? Well, it all comes down to a simple but really powerful ratio. See, we know exactly what percentage of that silver halide's weight comes only from the halogen we're hunting for. That fixed ratio, which is based on the known atomic masses of the elements, is what we call our gravimetric factor. We just multiply that factor by the weight of the evidence we collected, and then we compare it to the weight of the sample we started with. It's a really slick way to translate the weight of our evidence into the final answer. Okay, so to make this totally concrete, let's define our two key variables. First up, we have M1. That's the mass of the evidence itself, the final dried silver halide precipitate that we've so carefully collected. And the other variable, M, is simply the mass of the mystery compound we started with at the very beginning. Everything we do from here on out just connects these two simple weights. Okay, Siri is great, but let's see this in action with a real case study for bromine. The lab data on the left shows we started with 0.15 grams of an organic compound. That's our M. After running it through the Carius method, we collected 0.12 grams of silver bromide. That's our M1. Now for the math. We know the molar mass of silver bromide is 188. And of that 188, exactly 80 comes from the bromine atom. So we plug those numbers into our formula. It's 80 times 0.12 divided by 188 times 0.15. You run the numbers, multiply by 100 to get a percentage, and boom, our original compound was 34.4% bromine. Case closed. All right, let's grab our next case file, sulfur. Now, the beautiful thing here is that the core strategy, oxidize, precipitate, calculate, stays exactly the same. We're just going to swap out our reagents to target a completely different element. For sulfur, the process starts pretty similarly. We oxidize the organic compound, and in doing so, all the sulfur gets converted into sulfuric acid. Now we need to turn that into a solid we can actually weigh. So we add a solution of barium chloride. This causes a reaction where the sulfate precipitates out as barium sulfate, or BaSO4. It's this dense, white solid that's super easy to filter, dry, and weigh to get its mass. And this is just a perfect example of the power of these ratios. We know the atomic mass of sulfur is 32. We know the molecular mass of our final barium sulfate is 233. So our special gravimetric factor for sulfur is always going to be 32 divided by 233. Let's run the numbers for this new case. We start with 0.157 grams of a compound, and we end up with 0.4813 grams of barium sulfate. The calculation is a breeze. 32 times 0.4813 divided by 233 times 0.157 and then times 100. The result? 42.10% sulfur. See? It's the exact same logic, just with different players.
All right, time for a couple of quick-fire cases. First up, we've got phosphorus. And this one's pretty interesting because it actually gives the chemist a choice. Two different but equally correct paths to get to the answer. So just like before, we oxidize the organic compound, which converts all the phosphorus into phosphoric acid. But from here, the analyst gets to choose their own adventure. They can add something called ammonium molybdate to get this big, complex yellow solid. Or they can use what's called a magnesium mixture to form magnesium pyrophosphate instead. Each path leads to a totally different final solid, with its own unique mass and its own unique gravimetric factor for the final calculation. Pretty cool, right? And now for our last and honestly most notoriously tricky element, oxygen. For a long, long time, the easiest way to find oxygen was, well, not to find it at all. It's called the method of difference. You find the percentage of every other element, carbon, hydrogen, whatever, add them all up, and just subtract from 100. Whatever's left over must be the oxygen. It's clever, for sure, but it's really just an estimate. For a truly definitive answer, chemists had to develop a much more complex, direct method. The direct method is this really neat chain reaction. First, you have pyrolysis, which is basically just heating the compound in the absence of air. This breaks it apart and releases all of its oxygen as a gas. Second, that gas gets passed over red-hot carbon, which converts all the oxygen into carbon monoxide, or CO. And finally, that CO gas is passed over another chemical that adds one more oxygen, turning it into easily measurable carbon dioxide, CO2. It's an absolutely brilliant way to convert every single oxygen atom from our original sample into a completely different molecule that's easy to trap and measure. And the real magic here is in the chemistry. When you write out and balance the equations for that whole reaction chain, the carbon monoxide in the middle just perfectly cancels out. And what you're left with is this elegant conclusion. For every 1 mole of oxygen gas, which weighs 32 grams, that goes into the system, you get exactly 2 moles of carbon dioxide, weighing 88 grams coming out the other side. And that, right there, gives us our crucial gravimetric factor for the final calculation, 32 over 88. So we've gone through all these classical methods, and they're elegant, they're foundational, and as you can probably imagine, they are incredibly time-consuming and take a ton of skill to get right. So it's really no surprise that technology has completely changed the game in the modern lab. So meet the modern-day hero of elemental analysis, the automated CHN analyzer. This machine, and others like it, basically takes the entire process we've been talking about and automates it. It handles the combustion, the separation of the gases, and the detection, all inside one compact little box. And the advantages are just incredible. First off, you only need micro quantities of your sample. We're talking 1 to 3 milligrams, which is a tiny fraction of what chemists needed before. Second, the whole thing is completely automated, which gets rid of all those delicate manual steps and the potential for human error. And best of all, instead of spending hours and hours in the lab, you get a precise digital readout of the carbon, hydrogen, and nitrogen percentages in a matter of minutes. It's a total game changer. So, to wrap things up, let's just consolidate the key mathematical tools we've put together today. This is really the heart of the classical chemical detectives toolkit. Now, if you look at all these formulas together, you can see they all follow the exact same logic. It doesn't matter if it's for halogens, sulfur, phosphorus, or oxygen, the calculation is always built around that gravimetric factor, that fixed ratio of our target element's mass to the mass of the final solid we weighed. You just multiply that by the evidence you collected and divide by what you started with. This sheet right here is the ultimate summary of how we translate a physical weight in the lab into a precise elemental percentage. So, we've cracked the code. We know what our mystery compound is made of. We've got its elemental formula. But, this just leads to the next, even bigger question. Knowing you have, let's say, 6 carbons, 12 hydrogens, and 6 oxygens is one thing. But knowing how they are all connected together in 3-dimensional space to form a specific molecule, well, that's the next great mystery to solve.